Field instrument deployment for operational integrity and lifecycle maintainability. Preference for transmitters over discrete switches. Wherever analog or digital data is required for control, indication, or diagnostics, 4 to 20 milliamp transmitters are preferred over discrete field-mounted switches. Transmitters offer lower failure rates, better accuracy, and enable condition-based maintenance via signal analysis. Direct-mounted switches, e.g. pressure switches, are only permitted with principal approval and must be justified by application constraints such as cost, legacy system compatibility, or extreme simplicity. Visual coding for functional clarity. All IPF trip initiators, CL1 or higher, must feature a red finish to distinguish them from standard process instruments. Instruments in oxygen service must be finished in yellow per safety marking standards. All other plant-mounted instruments may follow the manufacturer's standard color, with red and yellow excluded to avoid confusion with safety-critical devices. Compliance with pressure boundary integrity. Inline instrumentation must meet or exceed the pressure temperature limits of the piping class or equipment to which they are attached. This includes sensor housings, flanges, bolting, and wetted parts. Certification and mechanical ratings must be traceable and verifiable. For equipment with no piping class, e.g. vessels, design pressure and temperature ratings must still govern selection. Integral and remote indicators for operator interface optimization. Where local indication is essential for field operator action, an indicator, either integral to the transmitter or remotely mounted, must be provided. The indicator's location must offer clear sight lines from the operator's standard working position, especially during manual valve operations, startup sequences, or field checks. If the transmitter includes an integral indicator not required for operations, it must be treated as invisible in the PEFs and not factored into display requirements. If clear visibility cannot be achieved through integral design, a remote receiving indicator is mandated. In all cases, indicators must present values in engineering units, matching DCS scale and operator convention. Where no operational field check is expected and no local interface is needed, blind transmitters are preferred for cost and simplicity. Their use also minimizes entry points for moisture, dust, and EMI. Instrument design must withstand full range of process and environmental extremes. Pressure and temperature limits for all pressure-containing parts in plant instruments must fully match or exceed the host system. For inline instruments, e.g. control valves, inline flow meters, this means full compliance with the assigned piping class, including transients and abnormal conditions. For online instruments, e.g. transmitters connected via impulse lines, the pressure-containing components must meet the same standards unless isolated by certified block valves. In such cases, limits must match the design pressure of the equipment, not necessarily the full class rating. Differential pressure instruments must be able to withstand full static pressure in both directions, accounting for possible misconnection, venting imbalances, or maintenance error. Instruments exposed to vacuum must be specified with absolute pressure tolerance and materials rated for subatmospheric service. For temperature extremes, e.g. Cryogenic or high-temp reactors, process limits must include startup, shutdown, and upset conditions, not just steady-state operation. Specification documents and requisitions must clearly define upper and lower mechanical limits, not just the calibrated operating range, to prevent mismatch between installed conditions and vendor assumptions. Material selection strategy to match process severity and corrosion risk. Instrument materials must be selected with the same rigor as process piping and equipment, ensuring compatibility with fluid chemistry, mechanical stress, temperature, cycling, and environmental exposure. Selection begins with the baseline assumption of AISI 36L stainless steel for all wetted components in clean or mildly corrosive services. However, this general standard is not universally suitable and must be reevaluated for each application based on actual fluid behavior and long-term exposure. For systems with chloride-bearing water in carbon steel lines, 3/16 L may be subject to pitting or stress corrosion cracking, particularly under stagnant or warm conditions. In such cases, higher alloy steels, specialty stainless grades, or non-metallic linings may be required. All stainless steels must be resistant to intergranular corrosion, verified per STAR ASTM A262 Practice E, and meet the piping class requirements for pressure containment. Inline instruments must match or exceed the pressure, temperature, and corrosion requirements of the piping class into which they are installed. This includes orifice plates, flow tubes, diaphragms, and sensor housings. Mounting gaskets, bolts, and flanges fall under mechanical scope but must be cross-verified for chemical compatibility. Impulse line materials must conform to DE 32.3710.11-Gen, typically stainless steel, and must be consistent across a loop to avoid galvanic corrosion. For control valves, D 32.36.01.7-Gen governs material selection of valve body, trim, and accessories. Special cases demand specific material prescriptions. Sour or wet H2S service. All wetted parts exposed to water or condensate must comply with ISO 15156 for production and gas treatment plants, or NACE MR 103 for refineries and chemical plants. Materials must resist sulfide stress cracking under operating pressure, temperature, and hydrogen partial pressure. Hydrogen fluoride HF alkylation. Wetted parts must be Hastalloy C276 with careful zoning of HF-specific and non-HF service areas to avoid overapplication. Only designated plant sections are typically subject to this requirement. Chemical plants with high Mo-alloy piping for equipment constructed of Incolloy 825 or Hastalloy, instrument bodies and wetted elements, e.g. diaphragms, manifolds, must use matching or superior alloys to avoid localized attack and maintain material compatibility. Strong reducing acid service, e.g. pure HCl or H2SR, Hastalloy B2 is required for wetted parts. Tantalum is specified for pressure sensing diaphragms. Application is limited to cases where acid concentration, purity, and temperature create aggressive reduction environments. Oxygen service, instruments must conform to DDEP 31.10.1131 Gen. Acceptable diaphragm materials include 3,6R and Elgiloy, with Elgiloy requiring a verified low-carbon variant to avoid weld decay. Systems above 21% O2 by volume or with air 50 bar G are considered oxygen service by default and must follow full cleaning, compatibility, and tagging protocols. For hydrogen-containing services, gold-coated diaphragms are mandatory when hydrogen partial pressure 7 bar A at 30 degrees Celsius or in any wet H2S application due to hydrogen diffusion risk. For instruments exposed to 100 degrees Celsius in these services, additional approval is required due to limitations of gold coating stability. All material selections must be clearly marked on equipment and referenced in datasheets and certification packages. This prevents misapplication, supports audit readiness, and reinforces traceability from engineering through installation. Diaphragm seals for isolation, accuracy, and maintenance in difficult services. Diaphragm seals serve as critical protective barriers between sensitive measurement elements and aggressive, viscous, or high-temperature process fluids. Their primary role is to isolate the instrument from conditions that would otherwise degrade accuracy, cause plugging, or exceed material or thermal limits. Diaphragm seals must be integral to the instrument design and specified as a unified assembly, including sensor, seal, and fill system, to ensure consistent performance and factory calibration. Applications justifying diaphragm seals include viscous, waxy, or plugging-prone fluids, e.g. slurries, polymerizing streams, coke-forming processes, where purging or flushing is either unreliable or labor-intensive. High-temperature process media that exceed transmitter or gauge temperature ratings, where capillary isolation prevents thermal damage. Interface measurements in small span ranges lies at 50 millibar, where traditional impulse lines are unstable or unresponsive. Seal size and geometry must match application needs. Typical DN 80 to 100 HAST seals are required for differential pressure-based level measurements, providing sufficient diaphragm area for responsiveness without sacrificing structural strength. For pressure transmitters, smaller seals may be used provided performance criteria are met. All seals must be welded assemblies. Threaded joints are prohibited to eliminate leak paths and maintain integrity under thermal cycling and vibration. Capillary tubing requirements. Remote seal systems must use 316L Stainless steel capillaries, mechanically armored and flexible stainless steel spiral or braided sheaths. Minimum length is start 1 meter, and when dual seals are used for differential pressure applications, capillary lengths must be identical to prevent thermal offset or signal imbalance. Process connections must also be located on the same side of the equipment to maintain hydrostatic symmetry. Thermal considerations for capillary installations. In outdoor or solar exposed areas, thermal insulation or tracing may be required to mitigate ambient temperature swings, which can cause fill liquid expansion and zero drift. All insulation must be UV stable and reflective, with black insulation explicitly prohibited due to solar absorption. In Arctic or fluctuating climates, temperature stability of the seal fluid is critical to avoid signal distortion or diaphragm damage. Seal filling liquids must be process compatible and environment safe. Seal liquids must be selected in collaboration with the process design team and verified with the instrument vendor. Criteria include compatibility with process fluid in the event of diaphragm rupture, viscosity and thermal expansion properties over the full design temperature range, environmental and personnel safety in case of release, e.g. non-toxic, non-flammable, stability under vacuum or pressure transients, especially in wet leg level applications. In vacuum service, transmitters must be mounted at least 50 centimeters below the bottom process tapping to ensure a minimum head pressure at the sensor. This ensures functionality under static vacuum conditions, as most transmitters require 35 millibar A to operate reliably. Handling, installation, and calibration provisions. Seal systems are inherently fragile and heavy. They must be mechanically supported during transport, installation, and operation. Protection plates must cover diaphragms until final installation, and all gasket selection must follow vendor-specific torque and sealing surface requirements. For accurate calibration and maintenance, test connections must allow for in situ zero span checks under live process pressure in compliance with DE 32.37.10.11-Gen. Diaphragm seals must be treated not just as accessories but as engineered extensions of the measurement system, critical to delivering stable, accurate, and safe performance in process environments where direct sensing is not viable. Accessibility engineering to ensure maintainability, safety, and operational uptime. Instrument accessibility must be engineered with the same diligence as process design. It directly impacts field safety, maintenance effort, and instrument uptime. Accessibility is not just about physical reach. It defines whether routine calibration, inspection, and troubleshooting can be performed without scaffolding, crane intervention, or process shutdown. 4 standardized accessibility classifications must guide layout decisions. Permanent accessibility. The instrument is within 1.7 meter vertically and 0.5 meters horizontally from a safe permanent walkway, grade, or platform with no obstructions. This is the target condition for all instruments requiring routine calibration, frequent manual checks, or test intervals 2 years, e.g., IPF devices, flow transmitters, level alarms. Limited accessibility. Instruments located between 1.7 meters and 4.0 meters high, or up to 1.0 meters offset, accessible only by ladder or mobile platform. This is permissible for indicators or transmitters not requiring routine intervention, provided they are visible or maintainable from below using safe, approved methods. Poor accessibility. Instruments located OI 4.0 meters high or requiring temporary structures, e.g. scaffolding, cranes, or removal of insulation/equipment equipment, to access. These should be avoided unless dictated by process layout or safety constraints. Poorly accessible instruments must be justified and mitigated through redundancy, remote diagnostics, or extended calibration intervals. Inaccessible. Any instrument that cannot be safely accessed during plant operation, either due to physical obstruction, high radiation, toxic atmosphere, or requirement for process shutdown. Such installations are non-compliant by default and must be re-engineered or explicitly approved by the principal. Accessibility must be evaluated early, during nozzle placement, piping routing, and platform design. Poor access is not a layout inevitability, but often a result of avoidable late-stage decisions. For example, relocating a nozzle or revising an impulse takeoff can shift an instrument from limited to permanent access with zero-cost impact if addressed early. Instrumentation that is inaccessible is not maintainable, and a non-maintainable instrument is a failed design. Accessibility must therefore be embedded as a design requirement, not treated as a post-construction workaround. Strategic instrument location for functional accuracy and field maintainability. Instrument placement must serve dual objectives: accurate representative measurement and safe, efficient access for operation and maintenance. Location is not arbitrary. It must reflect process conditions, mechanical constraints, and human interaction. For online instruments, such as pressure, level, and flow transmitters connected via impulse lines or tappings, placement must be near the process takeoff point to minimize impulse line length and response lag, free from heat, vibration, and obstruction. Position for clean, direct routing of tubing without sharp bends or unsupported runs. For measurement integrity, placement must avoid nozzle impingement zones or vortex areas, locations near pump suctions, control valves, or elbows that may distort flow or pressure, high points in liquid lines, gas pockets, or low points in gas lines, liquid traps that introduce measurement error. Field readability and physical access are equally essential. Local indicators must be visible from operator working positions, especially for equipment requiring manual intervention, backlit or shaded if subject to glare or poor lighting conditions, readable from walkways or platforms without stretching, leaning, or unsafe postures. Heavy equipment, e.g. control valves, displacer chambers, turbine meters, must be installed in areas accessible by mobile or fixed lifting equipment. Where mobile access is not feasible, permanent lifting provisions, beams, davits, must be integrated. Sufficient clearance around instruments must be preserved for removal of covers, enclosures, and flanges, extraction of orifice plates, thermowells, or displacer elements, rotting of impulse lines, and draining of chambers. Special requirements apply for instruments handling toxic fluids, high-pressure hydrocarbons, or corrosive agents. Their layout must minimize personnel exposure during maintenance, include clear labeling, venting, and isolation facilities, avoid installation near walkways or escape routes without protective shielding. While modern transmitters offer remote diagnostics and extended calibration intervals, that does not negate the need for strategic placement. Every instrument should be both operationally accurate and physically maintainable, a design standard that must be enforced, not assumed. The minimum accessibility standards provided in Appendix 3 serve as a baseline, but good design aims higher, seeking practical, cost-neutral layout improvements wherever feasible. An instrument that's safe to approach, easy to inspect, and correctly positioned is one that will remain reliable throughout its service life. Protective shades for thermal stability and electronic longevity in sun-exposed installations. Field-mounted electronic instruments exposed to direct solar radiation, particularly in tropical, desert, or equatorial environments, require protective shading to maintain signal stability, electronic integrity, and calibration accuracy. Solar heat gain can lead to zero and span drift in analog or digital transmitters, thermal cycling of housings and internal electronics, elevated failure rates due to aging of seals, LCDs, and circuit boards. Protective shades mitigate these effects by reducing localized heating and preventing one-sided radiation exposure that induces thermal asymmetry in enclosures. Shades also serve a secondary function as rain shields, particularly important during heavy tropical downpours, where sudden cooling and water ingress can compromise unsealed or poorly ventilated enclosures. In such cases, shades help prevent internal condensation that leads to corrosion or signal degradation. Shade design must be mechanically stable and resistant to wind uplift or vibration. Allow natural air convection around the instrument housing. Be made of UV stabilized, corrosion resistant materials, e.g. aluminum with powder coating, stainless brackets. Be mounted in such a way that they do not obstruct access to display screens, terminals, or adjustment points. Where instrument designs do not include vendor-provided integrated shades, or where non-standard supports or brackets are required, e.g. for inline flow meters, radar-level instruments, displacer chambers, these must be shown explicitly on detailed construction drawings. Their installation must be treated as part of the mechanical scope, not as a temporary or field improvised addition. Protective shading is not a cosmetic accessory. It is a functional requirement in regions where instruments are routinely exposed to extreme solar load. Omitting this detail leads to measurement instability, accelerated component aging, and unnecessary lifecycle maintenance. As such, sun shielding must be treated as an integral part of environmental hardening in instrumentation design.